This is FRM Part 1, Book 2, Foundations of Risk Management, and Chapter 3 called Distributions. And for me personally, this could have been called everything that I learned back in mathematical economics and my econometrics classes during my PhD program. Let's go see what it means for you by looking at these learning objectives. Now, the good news for you guys is that there is no calculate, there is no compute as those action words. So what you're going to have to do is describe. Look at those bottom three. But the first one is really important, I think. Distinguish the key properties among the following distributions. So we're going to take a look at all of those distributions, and then we're going to have to find some similarities and some differences between and among all of those things. We'll have to describe the Central Limit Theorem. We'll have to describe independent and identically distributed random variables, and we'll look at a mixture distribution in one of those final slides. All right, let's start with the uniform distribution. This is a distribution that has equally likely values over a range of possible outcomes. All right, so look at the graph there. For a uniform distribution, we start on the left-hand side at 0, and we work all the way up to x, which is this this random variable. Could be almost anything. But the interesting thing about this random variable is that it has a minimum value of alpha and a maximum value of beta. So remember, there are no values that fall between 0 and alpha, and there are no values that fall between beta and, whatever that big number is over on the right. The classic example of a uniform distribution is just rolling the dice. You have one in your hand, you roll it, and what can happen? You can get a 1 or a 2 or 3 or 4 or 5 or a 6. So the chance of getting any one of those is 1/6. So notice in that bottom bullet point, I have written there that the values from alpha to beta are equally likely. So rolling the dice, that should make perfect sense. There's the formula for the probability density function and the mean and the variance. And so if we just kind of do some quick math with the roll of the dice, what do you get? The mean is a 1. What's the lowest one? Is 1, right? The highest one is 6. So 1 plus 6 is 7 divided by 2. So the mean is 3.5. I mean, that really doesn't make any sense. You're never going to roll a 3.5 unless you're in some movie and they fix the dice. And then the variance is going to be, well, what would that be? 6 minus 1 is 5. Squared is 25 divided by 12. So that's about, that's about 2, right? And the square root of 2 or 2 something is, 1.7 or 1.8. So that's how you can compute the mean and the variance of a uniform distribution. Another example is the amount of time in minutes that a client spends waiting for their turn to see a portfolio manager. Could be uniformly distributed between 0 and 15 minutes. How about a Bernoulli distribution? So this is a little bit more interesting because what we're doing here is that we have these values and we assign them just two possibilities. You can have a 1 or a 0, and a lot of times the 1 means success and the 0 means failure. For example, you have a bank, right? And what can the bank do? The bank can either succeed or the bank can fail. Now, of course, when you do credit analysis for a bank and you look at Moody's or Standard & Poor's ratings, you have all these different ratings. And so there's shiftiness in between and among all those different kinds of grades. But here with the Bernoulli distribution, we're just going to call these success or failure. And they don't really have to be success and failure labors. They really don't have a literal interpretation all the time. It could be almost anything. Let's look at the example there. Notice that we start at 0 and we go all the way to 1 because there has to be a 100% chance of something happening, right? And so in that example, the P is going to be equal to 0.7. So we have a 70% chance of success, or 7 out of 10 banks succeed and 3 out of 10 then fail. There are good formulas for the mean and standard deviation of the Bernoulli distribution. Notice the mean is p, and the variance has p in it as well, but it really is, kind of like multiplying two probabilities. How about some examples? In life insurance, success could mean death, failure could mean survival. How about company paying a dividend or paying nothing at all? If both of these events are equally likely, then the success, the P for the dividend is half, and the P for the no dividend is half. That should make sense. How about a binomial distribution? In fixed income analysis, in trying to value a bond or trying to put together some kind of interest rate path, a lot of times we put together a binomial interest rate tree or a binomial model to calculate the value of a fixed income security or even an option. But here we've got these sequence of n Bernoulli trials such that each trial is independent of each other. And the trials are identical, which means that that p-value has to be the same for all of the trials. And so that's why this thing is often called a sequence of n independent identical Bernoulli trials. And there's the formula for the number of successes in the trial. And so notice that notation with, kind of like the pre-superscript of in the end, and then the post-subscript of the x. That's that whole thing that we talked about before with the factorials in the numerator and the factorials in the denominator. And then we just multiply those by p times 1 minus p. So it's really kind of a probability weighted factorial ratio. Here's the mean and the standard deviation of a binomial distribution. The study guide has makes a point to mention that sometimes it's written as theta, little zero with the line in the middle. As far as I'm concerned, it doesn't really matter what kind of notation you use. But here's a good example. What is the probability that at least 9 out of a group of 10 banks who have been hit by a serious cash crunch will ride out the crunch if the probability of the bank surviving the crunch is 70%? So we've got the 70%. We know that. So P is 0.7. And so there's an application of the formula down there. So note, there's the formula with the 0.7 and the 0.3. So there's the P and the 1 minus the P. And then here, let me just go back to this formula in blue in the middle. So we raise it to the x, the p, and raise the 1 minus p to the n minus x. So that should make perfect sense there. 10 minus 9, and then 10 minus 10. And then each of those is preceded by that big old factorial formula there. The good news for you guys is that the learning objectives don't say calculate that 14%, but still, clearly going through the example helps us to distinguish and describe and do all that kind of stuff. How about a Poisson distribution? So this is a distribution models the number of events that occur in a specified interval over time. Okay, so these events occur one right after another in a well-defined manner. So the process has to have a series of discrete events. So they occur singly, like something happens over time, like customers walking into the bank, or an internet surfer clicking on a story. Now this is important. The average time between events is known. So you know what the average time. So like on average, you're going to have to wait 7 minutes. When I call my health insurance company, they always say the average wait time is between 4 and 7 minutes. And so this is what they're trying to say here. The timing of the events is random. And so this is important. Non-overlapping time intervals are independent. So this is the distribution that uses the Greek letter lambda. And there's the distribution formula at the bottom, where you've got to use your little e raised to the x button on the calculator. Now here's the interesting thing about the Poisson distribution is that if this random variable x follows this distribution, then both the mean and the variance are equal to lambda. Examples include number of clients arriving at a bank. I said something like that. Number of goals scored by a soccer team. Now, I'm not quite sure that all soccer goals follow this Poisson distribution. I know when my daughter played soccer, she played on a really bad team and they used to lose like 25-0. So I think that might throw everything out. Number of claims an insurance company receives per week or per month. And then, accidents here. So let's work through a quick example. Number of new clients a wealth management company receives in a month is distributed as a Poisson random variable with a mean of 2. So 2 a month, so that must mean that there are 24 a year. So the question is, calculate the probability that a company receives exactly, that's important, exactly 30 clients in a year. And so the two relevant, let me go back here. The two relevant variables in this process are the x and the lambda. So we're going to come back here. Where am I? Yeah, there at the bottom. So we've got this 24 distribution over 30 clients a year. We're going to divide by 24 factorial. And if you do all that math, and that's, crazy math in your calculator, so you have to have a calculator that has this many decimal places. So you get about, 3 or 4%. And that should make sense, right? If your average is 2 a month and you're going to average 24 a year, if you want to know what's the probability that you're going to receive something 6 more than that 24, I mean, it has to be a relatively low probability. How about the normal distribution, which we have talked about before? The normal distribution was developed about 150 years ago by this guy Johann Gauss. So the normal distribution, most people call it a normal distribution, but you can call it the Gaussian distribution. And the picture of it is the bell-shaped curve. And let me just remind you quickly, without offending any of you, that the bell-shaped curve is kind of like a mirror image of each other. If you put a mirror on, right down the middle, then it kind of looks like it's the exact same thing, which it is. You always put the mean in the middle, so there's the population mean. We use the notation, the Greek U, which is a mu, and that's the middle. And one of the interpretations is that that's, you can't really say this, but the values around the mu are the most likely outcomes. And then we move to the right by a standard deviation, and we move to the left by standard deviations. And it's interesting that you can add 1 and 2 and 3 and 4 standard deviations, and you can get certain predictive outcomes based on how far you're moving away from the mean. We'll talk about that in a few slides. There's the PDF. It is normally distributed. And so what we need to do is that in order for us to make this possible, to make this applicable, is we need to use the Z-table. And so there's that formula in the middle there in blue for the Z-score, which is just your sample value X minus the population mean, sample mean, minus the population mean. And then we divide by standard deviation so that we standardize it. So look, I've said this to you guys before, it is a standardized normal variable, which means that it has a mean of 0 and a standard deviation of 1. Now the z-value measures how many standard deviations. So let's try to figure this out. If we start with the mean right there in the middle, and we move out to the sides, what kind of probabilities? Remember, of course, the probability under the normal curve is 100%. So notice what this table tells us there, that if we go 1 standard deviation above and 1 standard deviation below, that's about 68.2% of all observations fall within 1 standard deviation of the mean. And then you move out a little bit further, you move out 1 more standard deviation, and you're all the way up. You're all the way up to something greater, right? You're up to, how about 95% of all outcomes fall within 2 standard deviations of the mean. And then within 3 standard deviations of the mean, it's it's about 99%. And so, in our finance research, we kind of assume the 68, the 95, and the 99. But as you can see, those significant digits are more than just being able to be rounded up. In my brain, this is the way I teach my students. Now here's a Z-table, so that if we're trying to figure out from a Z-score, what is the probability that our value is less than that particular, what's the example we got there, 0.45. So run your finger down the left-hand column till you get to the 0.4, then run your finger across the top till you get to the 0.05. So of course 0.4 plus 0.05, you're summing the vertical numbers with the horizontal numbers, you get 67.36%. Now notice my bottom bullet point there. For more probabilities more precise than the ones tabulated, interpolation is necessary. Of course, if you have Excel handy, it does it for you. How about a log-normal distribution? Think of it this way. We have this continuous random variable. It follows a log-normal distribution if you take the natural log of that continuous random variable, and that follows a normal distribution. A lot of times in financial research, we look at stock prices, at prices, as following this kind of a distribution. It is asymmetric, so that's important. And there's the probability density function, and there's the mean and the variance. There's what it looks like. It's bounded by 0. That's why we like to put it with asset prices. And then it goes all the way out. Notice that it doesn't ever actually hit the horizontal axis. And it clearly has a skewness to the right, where there are lots and lots of values that have prices of, like, oh, let me just pick a number. Like, if this is a bond, it could be 980 or 1020 or 1100 or 1400, depending on the relationship between yield and coupons. How about the student's T distribution? This is how I learned it back in graduate school. You can use the Z distribution for large samples, but when you get to kind of small samples, then each individual observation, each individual random variable contributes more and more to the distribution. And so the student's T is kind of like the distribution for small, really, really small samples. So look under the I there. Whenever you're using small samples less than 30, you have to use the T distribution. But what we know is that once you get to 30 and 40 and 50, the student's T distribution, it becomes the Z distribution. But you also have to use this when the variance is unknown. Now, the T distribution has lots and lots of similarities to the Z distribution. I mean, it is symmetric. But sometimes it's tall and thin, and sometimes it's wider than the normal distribution. Chi-square distribution. This results when independent variables with standard normal distributions are squared and summed. It's used in lots of hypothesis tests and determining confidence intervals. Bounded on the left by 0, and there is an importance, just like with the T distribution, because that sample is relatively low, the degrees of freedom are important. There's a picture of the chi-square distribution, and what you use the chi-square distribution for is the following. Let's suppose that you're trying to test between different characteristics inside of a population. For example, is age important in terms of voting results? And maybe you define age as somebody who is retired and somebody who is not retired. Or is gender important in voting results? Or is gender important in purchases? So you see, we're trying to make a determination if one group is more influential than another group inside of this distribution. And there's the test statistic. The F distribution is used when you have two independent random variables, X and Y, and you're trying to make a determination of whether there are things inside of those random variables that are equal. I mean, the classic example is you got this giant population and you take a sample here and a sample here, and you want to know, are the sample means the same? And so you use the F distribution. By the way, this was named after a dude named Fisher. Lots and lots of good finance stuff were guys by the name of Fisher. Irving Fisher did the whole inflation. There was Fisher's separation theorem with the Harry Markowitz stuff. Fisher seems to be a popular name. Notice in the blue box down there, it's used in the analysis of variance. And so this will always show up whenever you're doing like a multiple regression equation, and you get the results, and you've got the F value there. A mixture distribution is exactly what the name suggests, a mixture of two or more probability distributions. And so what happens is that, of course, with those PDFs, you can test if your random variable follows this distribution or that distribution. And a lot of times it nearly follows that kind of a distribution. That's why in finance we always say something like, stock returns tend to follow a normal distribution. I mean, they don't really, but they tend to. I mean, we know there's some skewness in there, and there might be some kurtosis in there, but they nearly follow. And so the problem is that when you're doing some extremely important research, like maybe medical research or maybe engineering research, and then you got to really find out what that distribution is. And so sometimes there's got to be a mixture. Central Limit Theorem, this is one of my favorite things that I learned way back in the old days. What this tells us is that once you increase the sample size, lots and lots of these other distributions, they tend to become the normal distribution. Notice in that one bullet point in finance, Central Limit Theorem is applicable when a normal distribution is used to justify the approximation of variables that have a financial impact. And that takes us through this chapter. We did lots of distinguishing and identifying and describing and describing.